Semigroups and their representations, Lecture 7, Inverse semigroups. Let us recall the notion of a regular element and a regular semigroup from the previous lecture. Let S be a semigroup. Recall that an element A in S is called regular, provided that there is an element B in S such that ABA is equal to A. Such an element B is usually called a pseudo-inverse of A. An element B in S such that ABA is equal to A and BAB is equal to B is called an inverse of A. Note that this is a very unfortunate terminology, and each regular element has at least one inverse. A semigroup in which each element is regular is called a regular semigroup, and if some D class of a semigroup contains a regular element, then each element of this D class is regular, and each L class and each R class inside this D class contains an idempotent. A typical example of a regular semigroup is a semigroup Tn of all transformations of an n-element set. Okay, let us move on to inverse semigroups. Definition: a semigroup S is called inverse, provided that it is regular and each element of S has a unique inverse. So since this inverse is unique, we can introduce a special notation for this inverse. For an inverse semigroup S and A in S, the unique inverse of A is usually denoted by A to the power -1. This is a very unfortunate notation, but this is a standard notation, so we will use it. So in reality, A to the power -1 is not an inverse in the group sense, it's an inverse in this semigroup sense. So we have A times A inverse times A is equal to A, and we have A inverse times A inverse is equal to A inverse. However, an inverse semigroup doesn't need to have an identity element, so the equalities of the kind A inverse is equal to the identity or A inverse A is equal to the identity, they usually do not hold, and even they do not make sense, as there is usually no identity element. A typical example of an inverse semigroup is a group where the inverse is our usual genuine inverse. So in a group, we always have A times A inverse is equal to 1, and A inverse times A is equal to 1, and consequently we also have the semigroup inverse identities A times A inverse times A is equal to A, and A inverse times A inverse is equal to A inverse. And in a group, conversely, if we have a semigroup identity A times A inverse times A is equal to A, we can multiply it with A inverse on each side and get both A inverse is equal to 1 and A inverse A is equal to 1. So in particular, the uniqueness of the inverse elements follows from the usual uniqueness of an inverse element in a group. So in some sense, inverse semigroups are some kind of semigroup generalizations of groups where the notion of inverse is slightly weakened. And a typical example of an inverse semigroup is the symmetric inverse semigroup, which we already have seen, but now let's look at it in more detail. So let X be a set. The symmetric inverse semigroup IS of X is the semigroup of all partial injections from X to X under the operation of composition of partial maps. So a partial map, that's a map from a subset of X to X. And this subset Y, it's usually called the domain of our map, F. Given two partial maps, F from Y to X and G from Z to X, the composition G after F is defined only on those elements A in Y for which F of A belongs to Z. And for all such A, the composition of G after F applied to A is defined as the usual composition G of F of A. Note that the inverse semigroup consists of all partial maps which are injective. Of course, they are injective when considered as maps from their domain to X. And of course, composition of two partial injections is obviously a partial injection. Now we claim that for any set X, the symmetric inverse semigroup IS of X is an inverse semigroup. Proof. Let Y be a subset of X and F an injective map from Y to X. Consider the set Z inside of X, which is defined as F of A, where A runs through all elements in Y. Consider the map G from Z to X, which is defined on an element F of A as A. So G applied to F of A is equal to A for any element F of A in Z. Note that this defines G uniquely because F is an injective map. Then directly from the definition, we have that F after G after F is equal to F, and G after F after G is equal to G. So in particular, G is an inverse of F in the semigroup sense, and so IS of X is a regular semigroup. We have just proved that each element of IS of X has an inverse in the semigroup sense. And in order to prove that it's an inverse semigroup, we need to prove that this inverse is actually unique. So this element G, which we constructed, that's a unique inverse of F. So let U be a subset of X and H, an injective map from U to X, such that H is an inverse of F. So F after H after F is equal to F, and H after F after H is equal to H. From the first equality, that F after H after F is equal to F, it follows that Z should be a subset of U. And for any element A in Z, the value of H on A should be equal to the value of G on A. That's because we also have F after G after F is equal to F. From the other equality, that H after F after H is equal to H, we have that H applied to U should be a subset of Y for this equality to hold, and for any element A in U, we need that F applied to H of A should be equal to A. Since H is injective, it follows that U is equal to Z, and H coincides with G on U, which is the same as Z, and this means that H is equal to G. So we have just proved that the inverse element is unique, so IS of X is indeed an inverse semigroup. Next, let us move to a characterization of inverse semigroups. Theorem: a regular semigroup S is inverse if and only if the idempotents of S commute. Proof: let S be a regular semigroup in which idempotents commute. Let A be an element in S, and let X and Y be two different inverses of A. Then we have seen that for each inverse, the product of the element with its inverse on any side is an idempotent. So AX, XA, AY, and YA are idempotents, and by our assumptions they all commute. So we have X is equal to XAX, because X is an inverse, A is equal to AYA, so this is equal to XA, YAX. Now we swap YA and XA, we get YA XAX. We collapse XAX to X, and we get YAX. So X is equal to YAX. Also, YAX is equal to YAYAX. That's because Y is YAY. Now we have AY and AX, we swap them, we get Y, AX, AY. Now we collapse the middle AXA into A, we get YAY, and this is equal to Y. And if we read this through, we get that X is equal to Y. So indeed, we have a unique inverse, and this implies that S is an inverse semigroup. Conversely, let S be an inverse semigroup. Let E and U be two idempotents in S, and let X be the inverse of E times U. Let us consider the element UXE. We claim that this is an idempotent. Indeed, uxe times uxe is equal to uxe. This is because x is an inverse of EU. So in the middle, xeux is equal to x. Moreover, uxe times EU times uxe, this should be xe. So e square is e, u square is u, we get uxe, and we just check that this is uxe. Similarly, EU times uxe times EU, so u square is u, e square is e, this is EUX EU, and this is EU because EU and x are inverse to each other. So uxe is indeed the inverse of EU. So we have the inverse semigroup, both x and uxe are the inverse, so it follows that uxe is equal to x. And in particular, x is an idempotent. So the inverse to the element EU is an idempotent. But we have an inverse semigroup, and x is the unique inverse of the element EU, and x is an idempotent, so EU is a unique inverse of x, and this means that EU is actually equal to x, and this is an idempotent. So the product of two idempotents of our inverse semigroup is again an idempotent, and this means that E of S, the set of all idempotents of S, is a subsemigroup. In particular, the product in the other direction, UE, is an idempotent as well. But now, UE, EU, UE is of course UE, UE, and this is UE because it's an idempotent, and similarly EU, UE, EU is EU, EU, which is EU. And this means that both EU and UE are inverses to EU. But then they coincide because we are in the inverse semigroup, and so the product EU is equal to UE. And this completes the proof of our characterization. Now let us look at idempotence of the symmetric inverse semigroup. So if we consider the symmetric inverse semigroup IS of x, where x is a set, then the partial injection f from some subset y to x is an idempotent if and only if f of a is equal to a for each a in the domain of f. So the idempotents of the symmetric inverse semigroup on x are exactly the identity maps on subsets of x. The composition of two such idempotents, of course, corresponds to the intersection of their domains, and in particular, the set of all idempotents in IS of x is naturally isomorphic to the commutative semigroup of all subset of x with respect to the intersection of subsets. Now let us look a little bit closer at idempotence of inverse semigroups. Recall that a partially ordered set is a mid semilattice if each pair of elements in this partially ordered set has a greatest lower bound, which is usually denoted by wedge. Proposition: for any inverse semigroup S, the set E of S of all idempotents in S is a mid semilattice with respect to the partial order less than or equal to, which is defined as follows: an idempotent E is less than or equal to an idempotent U if and only if EU is equal to E. So the mid here is given by the product. The mid of E and U is equal to EU. Proof. Let us start by checking the transitivity of this relation. So if E is less than or equal to U and U is less than or equal to V, then EU is equal to E and UV is equal to U. Hence, E times V is equal to EUV because E is EU, and this is equal to EU because UV is U, and this is equal to E because EU is E. And this means that E is less than or equal to V. Also, if E is less than or equal to U and U is less than or equal to E, then E is equal to EU, that's equal to UE, and this is equal to U. And this means indeed that our relation less than or equal to is a partial order. Now let's show that the mid of two elements, the mid of two idempotents, is given by their product. To start with, if we have two idempotents U and E, then UE times U is U times U times E, which is UE, and this means that UE is less than or equal to U. And similarly, UE is less than or equal to E. Also, if X is an idempotent in S such that it is less than or equal to both U and E, then X times UE is XUE, which is XE because XU is X is less than or equal to U, and XE is X because X is less than or equal to E. And this means that X is less than or equal to the product of U and E. And together this implies that the meet of U and E is indeed UE. Next, let us discuss conjugation of idempotents in inverse semigroups. Let S be an inverse semigroup. Lemma: for any element A in S and any element E in E of S, we have that the product AE times A inverse is an idempotent. Proof: consider the product AE A inverse AE A inverse. Note that A inverse A is an idempotent, and so it commutes with E. So our product is equal to A times A inverse A times E times E times A inverse. The first three factors collapse to A, then EE collapses to E, and we get AE A inverse. And this proves that AE A inverse is indeed an idempotent. Corollary: for any A in S and any E an idempotent in S, there are U and V idempotents in S such that AE is equal to UA and EA is equal to AV. So we can always pass idempotents through elements, but sometimes we need to change idempotents. Proof: define U as A times E times A inverse. And we know that it's an idempotent because of our lemma. Then U times A is equal to A times E times A inverse A. The idempotents E and A inverse A commute, so that's equal to A times A inverse A times E. The first three factors collapse to A and we get AE. And the second claim is proved similarly. Now we can define the so-called natural partial order on an inverse semigroup. Let S be an inverse semigroup. For two elements A and B in S, we define A to be less than or equal to B, provided that A is equal to B times A inverse A. Lemma: the following conditions are equivalent for two elements A and B in S. Condition 1, A is less than or equal to B. Condition 2, there is an idempotent E in S such that A is equal to BE. Condition 3, there is an idempotent E in S such that A is equal to EB. And condition 4, A is equal to A inverse B. Proof: since A inverse A is an idempotent, then 1 obviously implies 2, just directly from the definition. And the implications that 2 implies 3 follows from the previous corollary. We can move idempotents from right to left in the product. Sometimes we need to change idempotents, but 2 and 3 are defined as existence, so it works. Now, given 3, so we assume that A is equal to EB for some element E in E of S. We have that EA is equal to EEB, which is EB, which is A. And now we multiply with A inverse on the right, we get EA inverse is equal to A inverse. So this implies that A, which is equal to A inverse A, this is equal to A inverse EB, this is equal to EA inverse B, because E and A inverse commute, and this is equal to A inverse B. And this gives us exactly condition 4. Finally, let us prove that condition 4 implies condition 1. So assume that A is equal to A inverse B, and then of course A is equal to A inverse B times B inverse times B, and we commute the two idempotents. This is equal to BB inverse A inverse B. So let's denote the element B inverse A inverse B by U. And we know that that's an idempotent, because it's a conjugation of an idempotent A inverse. Then we have that AU is equal to A, and hence A inverse AU is equal to A inverse A. Therefore, B A inverse A is equal to B A inverse AU. This is equal to BU A inverse A. We swap the two idempotents. This is equal to B inverse A inverse B A inverse A. And again, we swap idempotents. This is equal to A inverse B inverse B A inverse A. We collapse the middle B part into just one B. So we get A inverse B A inverse A. And this is equal to A inverse A because of our assumption, and this is equal to A. And this shows that condition 4 implies condition 1 and completes the proof. Now we can write down explicit properties of our relation less than or equal to. So proposition, we have the following properties. First, this relation is a partial order. Second, if A is less than or equal to B, then A inverse is less than or equal to B inverse. 3. If A is less than or equal to B and U is less than or equal to V, then AU is less than or equal to BV. 4. For all idempotents E and U, E is less than or equal to U if and only if E is equal to EU is equal to UE. So this relation satisfies with the partial order which we defined on idempotents. And 5, if we have an element U which is less than or equal to some idempotent E, then U itself is an idempotent. Proof. If we have two idempotents E and U, then E is less than or equal to U if and only if E is equal to U, E inverse E. E inverse is E because E is an idempotent, so this is UEE, which is UE, and since they commute, this is EU. And this proves property 4. Next, if E is an idempotent and U is less than or equal to E, then U is equal to E, U inverse U, where U inverse U is an idempotent, which we denote by V. But then U squared, which is equal to EV, EV, the idempotents commute, so this is equal to EE, VV, and then this is equal to EV because both E and V are idempotents, and that's equal to U. So this means that U is an idempotent, proving condition 5. Next, if A is less than or equal to B, then A is equal to B A inverse A, and hence A inverse is equal to A inverse A B inverse. So since A inverse A is an idempotent, we have that A inverse is less than or equal to B inverse by the previous lemma, and this proves condition 2. Next, if A is less than or equal to B and U is less than or equal to V, then by definition A is equal to B A inverse A, and U is equal to V U inverse U. And therefore AU is equal to B times A inverse A times V times U inverse U. By the previous lemma, V times U inverse U is equal to XV for some idempotent X. And next, B times A inverse AX. So here A inverse AX is an idempotent, so we can move it past B and have YB for some Y in E of S. Therefore, AU is equal to YBV, and which implies that AU is less than or equal to BV, again by that lemma, and this proves our condition 3. So it remains to prove 1, that less than or equal to is in fact a partial order. So assume that A is less than or equal to B and B is less than or equal to C, then this means that A is equal to B times A inverse A and B is equal to C times B inverse B by definition. And so A is equal to C, B inverse B, A inverse A. And again by the lemma, because this B inverse B times A inverse A is an idempotent, we have that A is less than or equal to C, so our relation is transitive. Next, if we have A is less than or equal to B, and B is less than or equal to A, then we have that A is equal to B A inverse A, and B is equal to A B inverse B. So this implies that A B inverse A is equal to A B inverse B A inverse A, which is equal to B times A inverse A, and this is equal to A. And we also have that B inverse A B inverse is equal to B inverse B A inverse A, B inverse B A inverse. This is equal to B inverse A, B inverse B A inverse, which is equal to B inverse B A inverse, which is B inverse. And this means that the inverse of B is equal to the inverse of A, and so A is equal to B. Therefore, the relation less than or equal to is indeed a partial order, and this proves property 1. So this completes the proof of our statement. This partial order less than or equal to is called the natural partial order on the inverse semigroup S. And we know that we used heavily the properties that S is an inverse semigroup and not just a regular semigroup when we defined and looked at the properties of this order. Next, let us discuss D classes of inverse semigroups. Observation: if S is an inverse semigroup, then the map which sends A to A inverse is an anti-automorphism of S. Consequently, this map induces a bijection between the right and the left classes of X. Also, let us note that A is left equivalent to A inverse A because A is equal to A times A inverse A. And obviously A inverse A is A inverse times A. And similarly, A inverse is right equivalent to A inverse A, and together this means that A is D equivalent to A inverse. And so the map which sends A to an A inverse preserves all D classes. Corollary: for each D class D of an inverse semigroup S, the map which maps A to A inverse induces a bijection between the right and the left classes of this D class D. Next, a little bit more about idempotence in right and left classes. So let S be an inverse semigroup and R a right class of S. Proposition: the class R contains a unique idempotent, namely A times A inverse, where A is an arbitrary element of R. Proof: of course, we already know that A times A inverse belongs to R for any A in R, and of course each idempotent of R must be of such form. So we need to show that if A and B are two elements in R, then A inverse is equal to B inverse. So since A and B are R-related, A is equal to Bx and B is equal to Ay for some element x and y in S, or S upper 1. Hence, BB inverse is equal to y inverse A inverse, and A times A inverse times B inverse is equal to A inverse, y inverse, A inverse. Okay, so now we collapse the first three to A, we get y inverse, A inverse, and this is equal to BB inverse. And similarly, A inverse BB inverse is equal to A inverse by a similar argument, and this means that BB inverse is equal to A inverse, and that's exactly what we wanted to prove. So here is a consequence for the egg box diagram of an inverse semigroup. Each D class looks like a square. In particular, it has the same number of left and right classes inside of it. So each D class is of course regular because it's a regular semigroup, it contains an idempotent, and we can arrange the egg box diagram of this particular class such that the rows and the columns in this diagram are indexed in such an order which is respected by the map which sends A to A inverse. And then, so each L class and each R class contains an idempotent, and these idempotents then will align on the main diagonal of this picture. And the product of two different idempotents inside the same D class never belongs to this D class, it goes farther down in the order. Some additional problems and questions at the end. Problem question 1. Prove with all details that a partial injection is an idempotent if and only if it's the identity on its domain. Problem question 2. Prove that the inverse of A inverse is equal to A in any inverse semigroup. Problem question 3. Prove that the inverse of AB is equal to B inverse A inverse in any inverse semigroup. Problem question 4. Prove with all details that for any inverse semigroup S, the map which sends A to A inverse is an anti-automorphism of S. And problem question 5. Prove with all details that each left class of an inverse semigroup contains a unique idempotent. Thank you very much and see you next time.